afternoon, everyone. My name is Denise. Today, I will be how valve endothelial cells exposed to high flow oscillations can lead to valve interstitial cell calcification. So heart valves help us maintain proper direction of blood flow. However, they are subject to diseases such as calcific aortic valve disease, which is one of the most prevalent chronic heart problems today. And studies have shown that in the last 30 years, it has increased by 100% or more. And the result of a heart valve calcification is stenosis, regurgitation, and reduced cardiac output. The current treatment options for early and intermediate stages of calcific aortic valve disease are not available. Severe treatments include a valve prosthetic or mechanical valve replacement. However, valve prosthetic valves are prone to recalcification, which requires multiple operations, and mechanical valves require the patient to be on lifelong anticoagulants. Both are invasive and therefore are limited to a selective patient subset. Most aortic valves consist of 3 leaflets. Some people are born with 2, and some people are born with 4. The leaflets contain 3 different layers: the ventricularis, spongiosa, and fibrosa layer. The fibrosa layer faces the aortic side and mainly consists of collagen fibers. Ventricularis is on the faces the ventricular side and it's mainly composed of elastin fibers, and the spongiosa is sandwiched in the middle. So on the surfaces of these valves, you see that there are valve endothelial cells in red, and valve interstitial cells are sandwiched in the middle. As VECs reside on the surfaces of the valves and fixed in the middle layers, the VECs are subject to shear stresses. On the ventricular side, because of the valve structure, it is mainly subject to laminar and high shear stress, laminar flow with high shear stress. However, on the fibrosa side, the VECs on the fibrosa side are mainly exposed to oscillatory shear stress and low shear values. We know that in previous studies, low shear stresses causes lesions and calcification in the vascular system. And oscillatory flow with high calcium concentrations in the blood can trigger inflammation on the valve fibrosa layer. What we want to know is the relation between a precise flow oscillation and development of calcific aortic valve disease. So what is an oscillatory shear index? It is a measurement of flow disturbance which quantifies the ratio between forward shear stress and total shear stress. With the equation here, and the big T is duration of cycle, tau is the wall shear stress, and little t is time. And the OSI value is ranged between 0 and 0.5. So this is a picture or an animated picture of what different OSIs look like. As we can see, when OSI is 0, the flow is either in static or steady with no reversive direction of flow. But at OSI 0.25, we have some moderate flow oscillation, and at 0.5 OSI, we have a full oscillation. So the objective of my study is to correlate OSI with progression of calcific aortic valve disease. And we hypothesized that a combination of high OSIs with pro-calcific environment will promote aortic valve disease. So to test our hypothesis, we evaluate the paracrine signaling events, which is communication between the 2 different cell types, and specifically I'm looking at VECs and VICs and how VECs relay messages to VICs in terms of developing calcification. So the VECs will be subject to different OSIs, and we will further assess that, how they communicate to VICs that lead to disease. First, we cultured VECs. And commercially available VECs are obtainable with the specific required growth medium and the culture flasks. The VECs were then subject to a Bioflux shear assay system using 24 well plates that consist of 8 microfluidic channels per plate. And the VECs were subject to 48 hours of different OSIs. The OSIs are pictured here with 0, steady, low, 0.25, and 0.5 OSI. Upon termination of the VEC conditioning, we collected the media from the VEC groups, which I will now call this the original media. Then we placed a portion of this media into ultracentrifuge to isolate an exosome pellet. And after that, we isolated the pellet away from the supernatant by extracting the supernatant. And now we have 3 different groups, and all of them were added with pro-calcific ingredients to induce big calcification. So the pro-calcific ingredients are, 5% FBS, 1% pen strip, 1.8 millimolars of calcium chloride, 3.8 millimolars of sodium dihydrogen phosphate, and 0.4 units of inorganic pyrophosphate. And as mentioned earlier, these were added to induce big calcification. So now we have 3 different groups: the original group, the exosome pellet group, and the cytokine group. And after that, they'll be named these original EX and CY for short. So once we have the Beck media collected, the next thing is we purchased commercially available valve interstitial cells and expanded them in culture. So to simulate the paraffin signaling, we used the conditioned media from Beck's in all the flow groups to further culture VIGs, and the VIGs were conditioned in 7 days in these 3 different groups in a 24-well plate and static. We then used alizarin red staining to quantify the level of calcification in each of the wells, and used and also normalized it to the amount of protein secreted in each well. So in our first study, with the original pro-calcific Beck conditioned media, we see a decreased amount of calcification in the 0.25 OSI group compared to the fresh media group. And the fresh media here is a positive control where the VIGs were exposed to pro-calcific media, but that has no communication with the VIGs. And right here in the bottom row, we have the negative controls. And each of these groups are VIGs exposed to VEC communication media, but without the pro-calcific ingredients. And while there is no statistical significance across any of the flow groups, we do see a significant difference between the fresh media control and the 0.25 group. In our second study with the exosome pellet, we see a general decrease of calcification when the things were exposed to VEC communication, but there is no significant difference between any of these groups, even when compared to the fresh. And then in the next study with the pro-calcific cytokine supernatant, we see a significantly lower calcification between the fresh positive control and the static steady at 0.25 OSI. With everything is lower with the exception of 0.5 OSI. And if we compare the 0.5 with other flow groups, we also see a significant difference. So this is a summary of all the groups combined. I'd like to point out that in the non-exosomal group, which is also the cytokine group, we see a significantly decreased calcification compared to the positive control, except for the 0.5 OSI as mentioned earlier. And this probably suggests that high oscillations in combination with pro-calcific environment may be a cause to calcific aortic valve disease through a non-exosomal cytokine pathway. So that is something that we'll be testing. And so in the interest of cytokine communication, the next thing that we have is to assess possible calcific pathways triggered by the flow environments. And this list here are all the cardiovascular inflammatory cytokines. And we will use them as biomarkers and hopefully synthesize something in the future that intervenes with this if it does lead to a disease progression. And if you're interested in the next episode results, you can find me at the World Congress of Biomechanics this summer, and which will be held in my home country in Taiwan. Or alternatively, you can attend my dissertation on Zoom or in person. And I'd like to thank Dr. Hutcheson and Dr. Ramaswamy for this research, and thank you all for your attention.